Hello, dear friend, and welcome to the Sleepy Physicist. I'm so glad you're here with me tonight, or today, wherever you are in this vast, beautiful world. Before we float into the glowing embrace of our favorite neighborhood star, I'd love to hear from you. Where are you listening from, and what time is it there? Are you curled up in bed, ready to drift off, snuggled under a cozy blanket on the couch, or letting this play softly in the background while your cat carries out secret midnight missions in the shadows? If you enjoyed these gentle journeys through the cosmos and the quiet wonders of science, a soft tap on the like button and a kind subscription truly mean a lot. It helps keep this little sleepy corner of YouTube glowing warmly for nights to come. Tonight's story is about a star that never sleeps, quite the opposite of what this channel aims to do for you. While the sleepy scientist is here to help you unwind and let your thoughts settle, the sun is forever awake, always burning, always fusing tiny particles into the radiant warmth we often take for granted. A restless fire in the sky, tirelessly working so you can rest in peace beneath its light. We're going to explore nuclear fusion tonight, that slow, astonishing process powering the sun. Together, we'll drift down into its core, follow the winding, timeless journey of a photon, and marvel at the delicate dance of pressure, gravity, and light. There's no need to rush. Let the words settle over your thoughts like drifting stardust. I hope this video helps you relax and fall softly asleep. But if it ends up sparking your curiosity and you lie awake pondering hydrogen, nuclei, and ghostly neutrinos at 2 in the morning, well, there are far worse thoughts to keep you company in the quiet hours. At the very least, you'll greet sunrise a little wiser than before. So, get comfortable. Let your breathing slow. Okay, let's begin. Just so we're clear, nothing in this video is meant as medical advice. I am not a doctor. I'm simply a sleepy scientist, endlessly fascinated by stars that never take a nap. Once upon a time, about 4.5 billion years ago, a quiet cloud of gas and dust drifted through the darkness of space. There was nothing grand about it, mostly hydrogen with a little helium and faint traces of heavier elements, all floating together in a lazy cosmic haze. But, as we often learn, stillness does not mean nothing is happening. Sometimes it is the pause before everything changes. This cloud was part of a far larger molecular nebula, a cold, vast ocean of star-making material. And, as with many tales of the cosmos, it all began with gravity, that silent matchmaker of the universe. Gravity draws everything closer, whispering for particles to gather and huddle in its invisible embrace. Give it enough time, and the universe has more than enough, and gravity builds stars at some point. Perhaps, nudged by the shock wave of a distant supernova, this gentle cloud was stirred into motion. Slowly, parts of it began to collapse, inward, moving softly at first, then faster, swirling as they fell. What was once a lazy, drifting stretch of gas became something new, a protostar in the making. As the gas and dust fell inward under gravity's pull, the core grew denser and hotter. Imagine packing more and more people into a crowded room while cranking up the thermostat. Eventually, it becomes deeply uncomfortable. At the heart of this collapsing mass, pressure rose, temperature soared, and somewhere around 15 million degrees Celsius, a quiet miracle occurred. That was the moment the sun ignited. Not with a bang or a sudden burst, but with the calm, astonishing onset of nuclear fusion. Stars aren't fiery balls of flame, though it feels natural to think so. They're hot, they glow, and they seem to burn. But what happens in a star's heart is far stranger than fire. Fire is just a chemical reaction, atoms exchanging electrons and releasing energy. Fusion, on the other hand, is atomic alchemy. It's when nuclei themselves are pressed together so tightly that they merge, transforming into something new and releasing unimaginable energy in the process. In the case of our sun, it all begins with hydrogen, the lightest and most abundant element in the universe. Each hydrogen atom holds one proton and one electron, but deep within the sun's core, where heat and pressure are beyond comprehension. Those electrons are stripped away, leaving behind a churning sea of naked protons and ionized particles, colliding with unimaginable force under ordinary conditions. Two protons would repel each other fiercely, like two magnets with identical poles. But here, in the sun's furnace, pressure is so intense and protons move so fast that occasionally, just occasionally, they collide with such force that the strong nuclear force overcomes their repulsion and binds them together. And in that moment, fusion begins. The simplest and most abundant element in our universe is hydrogen. Strip it down to its essence, and it's just a single, tiny proton, one positively charged particle, floating in the vastness of space. Now, imagine gathering unimaginable trillions of these hydrogen atoms together in one place, say, the core of a star, and heating them to temperatures beyond anything we experience on Earth. Something fascinating happens. The intense heat strips away their electrons, leaving behind a swirling, flowing sea of free-floating protons and electrons, a state known as plasma. Within this roiling plasma, K-protons dart around chaotically, colliding endlessly under normal conditions. These protons would repel each other with fierce determination, like trying to push two identical poles of magnets together. Their positive charges keep them apart. But inside the sun, conditions are anything but normal. Temperatures soar to around 15 million degrees Celsius, causing protons to move at unimaginable speeds. Occasionally, they slam into each other with such force that their natural repulsion is overcome. And something extraordinary begins. Fusion. This process powering our sun is called the proton-proton chain. While the name might sound like a cereal for physicists, it's the very reason we feel sunlight on our skin or watch plants grow in quiet morning gardens. Here's how this cosmic dance unfolds. First, two protons collide with such intensity that one of them transforms into a neutron. This magical transformation is made possible by a process known as the weak nuclear force. Despite its name, it's strong enough to alter the identity of a subatomic particle. As the proton changes into a neutron, it emits two curious particles, a positron, which is like an electron's cheerful antimatter twin, and a neutrino, a ghostly, almost massless particle that barely interacts with the universe as it races away at near light speed. What remains is deuterium, special form of hydrogen with one proton and one neutron in its nucleus. This deuterium quickly finds another proton and fuses with it, creating helium-3, which holds two protons and one neutron. This fusion releases a gamma ray, a high-energy photon that begins its journey, bouncing endlessly within the sun. Finally, its helium-3 nuclei collide and fuse to form helium-4, with two protons and two neutrons in its heart. In the process, two extra protons are cast aside like spare pieces, returning to the swirling plasma to continue the fusion dance. It sounds like a complex ballet, and it is, yet this process happens constantly throughout the sun's core. Every single second, the sun fuses about 620 million tons of hydrogen into helium. In doing so, it converts roughly 4 million tons of mass into pure energy each second. That's like watching 4 million elephants vanish into light every single heartbeat, and even that image falls short of reality. But here's the intriguing part. This energy doesn't just rush out to space immediately. Photons created during fusion spend thousands, even millions of years bouncing their way through the sun's dense interior, absorbed and re-emitted in an endless journey before finally reaching the surface. By the time a single photon breaks free and races out into the cosmos, it may be older than all of human civilization. Consider for a moment the crushing environment where this occurs. The pressure at the sun's core is about 340 billion times the air pressure we feel at sea level. If you could somehow place a single postage stamp in the core, the force pressing down on it would equal millions of tons. It's not the sort of place any living creature could survive, not even for a moment. Matter behaves strangely under these conditions. Particles blur into a quantum haze, existing as both waves and particles, flickering between possibilities in ways that defy normal understanding. Yet, from this chaos emerges astonishing stability. The sun rises and sets, day after day, with near-perfect consistency. Its light is gentle and dependable, born from an interior filled with unimaginable violence and pressure. Fusion itself is incredibly efficient. When hydrogen fuses into helium, about 0.7% of its mass turns into energy. That might sound small, but when compared to burning coal or gasoline, where only a tiny fraction of a percent of mass becomes usable. Energy fusion is staggeringly effective and far cleaner. No smoke, no ash, no toxic remnants, just pure light, warmth, the sprinkling of neutrinos, unlike nuclear fission, where atoms are split apart, releasing dangerous byproducts. Fusion binds small nuclei together, yielding far more energy with far fewer risks. If humanity ever masters controlled fusion on Earth, it would become our ultimate energy source, sustainable, safe, and almost limitless. Yet, while we build enormous magnetic chambers and struggle to control fusion's fury in laboratories, the sun achieves it effortlessly, purely by existing with enough mass and gravity to make fusion natural and constant. It's humbling, too. Realize that even the sun has limits, though. For billions of years, it has been fusing hydrogen, and it will continue to do so for billions more. But eventually, it will run out of hydrogen in its core, shifting to helium fusion and briefly creating heavier elements before its final chapters unfold. For now, you can simply marvel at this quiet miracle happening above us, a clear fusion. A process so easy to overlook or misunderstand is one of the universe's deepest engines. It lights the stars, sculpts galaxies, and makes life possible on this small, gentle planet we call home. It's a beautiful paradox, a process so extreme and violent at the atomic level becomes the soft golden glow of sunset, or the warmth of spring morning sunlight on your face. Fusion is both furnace and gift, an ancient reminder that even the smallest particles, under the right conditions, can come together to create something astonishing, something bright, something that never sleeps. So, let your mind drift for a moment and imagine diving beneath the sun's glowing surface, not in a spaceship or some mythical heat-proof vessel, with your thoughts gently descending through golden layers into a realm of pure light and unimaginable power. Here, at the sun's secret heart, we find the quiet miracle that keeps the universe glowing. Imagine for a moment a small ball rolling toward a steep hill. In the ordinary world, it would roll up only so far before gravity pulled it back down. But in the quantum world, things don't always follow common sense. Instead of rolling back, the ball simply disappears from one side and reappears on the other. No digging, no drilling, just a graceful little hop to reality. Inside the sun's core, a similar miracle unfolds. Hydrogen nuclei, under normal conditions, don't have enough energy to overcome their mutual repulsion and fuse, But quantum tunneling allows them to slip through this barrier. It's a rare event when you think in probabilities, like tossing a million-sided dice and needing a specific number. Yet the sun is so vast, with so many hydrogen nuclei colliding every moment, that even these rare outcomes happen constantly. When fusion does occur and energy is released, it doesn't immediately beam outward in a straight line like light from a torch. Instead, it begins a long, tangled journey through the sun's inner regions. The photons born from fusion, gamma rays, don't travel easily. They are absorbed, re-emitted, and scattered in all directions by surrounding particles, playing a ceaseless game of cosmic pinball. This zone of photon chaos is called the radiative zone. and it acts like an immense, glowing fog. For a single photon to make its way through this region to reach the sun's outer layers can take anywhere from 10,000 to over 1,000,000 years, depending on its path. So, the sunlight that warms your face today began its journey when ancient mammoths wandered ice-covered plains, when glaciers carved valleys, and when early humans huddled around quiet fires under the stars. Eventually, after countless deflections and re-emissions, energy reaches the convective zone, the sun's outer third. Here, radiation is no longer enough to move energy efficiently. Instead, convection takes over. If you've ever watched a pot of soup boil, you've seen convection in action. Hot material rising, cooler material sinking, churning in an endless loop in the sun. So immense bubbles of hot plasma rise toward the surface, cool slightly, and sink back down again, stirring the outer layers in massive slow-motion waves. Each of these convective cells can span hundreds of thousands of kilometers, circulating energy from deep within to the sun's surface. This movement not only transports heat, but also gives rise to much of the sun's visible activity, sunspots, flares, and magnetic fields. But those wonders are stories for another quiet evening. Take a moment to appreciate the sheer scale of this structure. From its center to its surface, the sun stretches nearly 700,000 kilometers across, over 100 times the diameter of Earth. Yet the core, where fusion happens, occupies only about a quarter of the sun's radius. Even so, it is still large enough to fit 14 Earths lined up side by side. Above the core lies the radiative zone, extending out to about 70% of the sun's radius, and beyond that is the convective zone. Though fusion itself happens deep at the center, its effects ripple outward through every layer, shaping the sun's behavior and ultimately determining the warmth and light that reaches here on Earth. What's truly fascinating is that we can't observe any of this directly. There are no telescopes peering into the sun's hidden heart. Instead, scientists combine theories, computer models, and ingenious observations to unravel these secrets. One of their tools is helioseismology, a field that studies sound waves rippling through the sun. Just as geologists study earthquakes to understand Earth's interior, solar physicists observe the sun's oscillations to learn about its temperature, density, and inner layers. Another source of insight comes from neutrinos, ghostly particles created during fusion reactions. These neutrinos pass through the sun, Earth, and even our bodies without interacting, like silent messengers from the solar core. By detecting them, scientists confirm that fusion is indeed happening deep within the sun right now. Despite its complexity, the sun remains remarkably stable. It has burned steadily for over 4 billion years and will continue for billions more. This slow, patient process is the heart of life on Earth. Every tree, every flower, every breath you take owes its existence to the quiet fusion reactions unfolding far above. So next time you feel sunlight on your skin, pause for a moment. Behind that gentle warmth lies an ancient chain of events, hydrogen nuclei colliding in a sea of plasma, slipping through barriers with quantum grace, releasing photons that bounce their way outward over geological ages to reach you. The sun is more than just a bright disk in the sky. It is a cathedral of physics, a slow-burning miracle, a furnace, not a fire, but a fusion, calm, constant, and beautiful. If the sun had a recipe, it would sound almost simple. Take 4 hydrogen nuclei, place them under unimaginable heat and pressure, sprinkle in quantum mechanics, and wait. The result is a helium nucleus and enough energy to keep our planet warm, our oceans liquid, and our lives illuminated. This process, the proton-proton chain, is the sun's signature reaction. Despite its gentle name, it fuels the entire solar system. It transforms hydrogen, the simplest element, into helium, releasing energy that shapes winds, feeds forests, and gives rise to all life on this small blue world. Though each individual fusion event is rare and slow. The sun contains an unimaginable number of protons, ensuring that this quiet dance continues without pause. Every second, the sun converts about 4 million tons of mass into pure energy, enough to power life as we know it. It's humbling to realize that the light bathing your face today began with 4 tiny protons fusing together in a silent, quantum embrace deep within the sun's hidden heart. Long before you were born, the ball, instead of bouncing back, simply vanishes and reappears on the other side of the hill. No digging, no drilling, just an elegant little hop through space in the core of the sun. Quantum tunneling allows hydrogen nuclei to fuse even when they don't have quite enough energy to overcome their mutual repulsion on their own. It's a rare event, probabilistically speaking, but the sun is so large and full of hydrogen that even rare events happen constantly. It's like rolling a die with a million sides and needing to land on just one specific number. If you rolled that die trillions of times every second, still going to see that special number show up quite often. Once a fusion reaction occurs and energy is released, that energy doesn't immediately shoot outward like a flashlight beam. Instead, it begins a long and arduous journey through the sun's interior. This process is not straightforward. It's not even vaguely efficient. The gamma rays created during fusion ricochet off particles in the surrounding plasma, being absorbed, re-emitted, scattered, and bounced in every direction imaginable. It's as though each photon is playing the most confusing game of pinball ever devised. This inner region surrounding the core is known as the radiative zone, and it acts like an immense fog of particles. Light produced here can take an astonishingly long time to escape, anywhere from 10,000 to over 1 million years, depending on the particular path a photon takes. So, the sunlight we feel on our skin today began its journey when mammoths roamed the earth, when glaciers carved out valleys, when human ancestors huddled around fires. It is ancient energy just arriving. Eventually, after bouncing its way outward for a geological eternity, this energy reaches the next layer of the sun, the convective zone. It's here. The density of the sun has dropped enough that radiation alone can no longer carry energy efficiently. Instead, the sun relies on convection, a process we're all more familiar with. If you've ever watched a pot of soup boiling on the stove, you've seen convection in action. Hot material rises, cool material sinks, and the whole system churns in an endless loop in the sun's convective zone. Giant bubbles of hot plasma rise toward the surface, cool slightly, and sink back down again. This movement stirs the outer layers of the sun like a slow solar stew. Each convective cell can be hundreds of thousands of kilometers across. These massive, slow-moving rivers of plasma circulate energy from the deep interior to the outer layers of the sun. They also give rise to much of the sun's visible activity, sunspots, flares, and the solar magnetic field. But we'll gently save those wonders for another time. As we continue our mental descent, let's take a quiet moment to appreciate the scale of the sun's interior. From the center to the surface, the sun spans nearly 700,000 kilometers. That's over 100 times the diameter of the Earth. Yet the core itself, is the region where fusion actually occurs, is relatively small in comparison. It extends to only about 1/4 of the sun's total radius, or roughly 175,000 kilometers. That's still enormous by our standards. Roughly 14 Earths lined up side by side, but in the vastness of the sun, it's just the innermost chamber of a much larger, more intricate structure, the radiative zone, where energy meanders outward through photon pinball, extends from the edge of the core out to about 70% of the sun's radius. Beyond that lies the convective zone, which takes up the final 30%. So while fusion only happens in the deep center, the effects ripple outward through every layer, shaping the sun's behavior and ultimately determining how its energy reaches. One particularly fascinating thing about the sun's interior is that we can't observe it directly. There are no windows into the core, no telescopes that can see fusion in action. Yet remarkably, we've learned an enormous amount about this hidden world. Scientists use a combination of theoretical models, computer simulations, and observational data to peer beneath the sun's surface. One of the most powerful tools for doing this is helioseismology, a field that studies sound waves traveling through the sun, just as geologists study earthquakes to learn about Earth's interior. Solar physicists observe ripples and oscillations on the sun's surface to infer what's happening deep inside. These waves are caused by turbulent motions in the convective zone, and they carry subtle information about the density, temperature, and composition of the layers they pass through. Another important source of information comes from solar neutrinos. These ghostly particles are created during fusion reactions and pass through the sun and everything else almost entirely unimpeded. They zip through planets, people, and even lead shielding as though those obstacles weren't there. By detecting solar neutrinos here on Earth, scientists can confirm that fusion is happening in the core and even estimate the rate at which it occurs. Our understanding of the sun's interior is constantly evolving, but one thing is certain: it is a dynamic, complex, and utterly alien environment. There is no solid surface, no clear boundary lines, just layer upon layer of plasma, pressure, and heat, each with its own role to play in the delicate symphony of starlight. And yet, despite all this complexity, the sun remains wonderfully stable. It has been fusing hydrogen and shining steadily for billions of years, and it will continue to do so for billions more. This slow and steady process is not just the engine of the sun, it is the quiet heart of life on Earth. Every tree, every flower, every breath we take owes something to the energy generated in that distant core. So the next time you feel the sun on your face, pause for a moment. Behind that warmth is a chain of extraordinary events, particles colliding in a sea of plasma, quantum tunneling across barriers, and ancient photons emerging from a million-year journey through fire and gravity. The sun is not just a bright light in the sky. It is a cathedral of physics, a slow-burning miracle that never sleeps. It was opposed by a new force, the outward pressure, generated by the energy released in fusion reactions. When hydrogen nuclei fuse into helium in the sun's core, they release an enormous amount of energy in the form of photons, neutrinos, and kinetic energy. These energetic particles exert pressure on the surrounding material, pushing it outward. This pressure is not a simple blast or an explosion. It is a steady, persistent force, like steam building up in a sealed chamber. It's what keeps the outer layers of the sun from falling inward and what maintains the sun's spherical shape over billions of years. Hydrostatic equilibrium is achieved when the inward pull of gravity is exactly balanced by the outward push of pressure at every point within the star, not just at the surface, but in every layer, from the blazing core to the wispy corona. It is a dynamic balance, not frozen, but continuously maintained as conditions shift and evolve. If fusion were to suddenly stop, pressure would drop and gravity would win. The sun would begin to contract. Fusion somehow accelerated out of control, pressure would rise and the sun would begin to expand. But because the processes are so finely tuned, the sun remains stable. This is the cosmic version of walking a tightrope, except instead of balancing on a wire, it's balancing an entire star. What's remarkable is just how sensitive this balance is. The rate of nuclear fusion in the sun's core is governed by the temperature and density there. A small increase in core temperature can lead to a disproportionately large increase in the rate of fusion. This, in turn, increases the pressure and causes the core to expand slightly, which lowers the temperature and slows the fusion rate. Likewise, the temperature drops, fusion slows, pressure decreases, and gravity causes the core to contract, heating it back up and restoring the balance. This feedback loop keeps the sun's output remarkably steady over time. It's a self-regulating system, like a cosmic thermostat, always adjusting to maintain equilibrium. And it works. The sun's luminosity has increased by only about 30% over the past 4 billion years, a slow and steady rise that has given life on Earth the stability it needs to thrive. But what would happen if this balance were disrupted? Let's imagine, purely as a thought experiment, that fusion in the sun's core were to stop suddenly, perhaps because the hydrogen fuel had been exhausted, or because a fictional space wizard snapped his fingers. Without fusion, there would be no more energy pushing outward. The core would no longer resist gravity's pull, and it would begin to collapse as the core contracted. It would heat up, because when you compress a gas, it gets hotter. This increased temperature might ignite a new round of fusion reactions involving helium or other heavier elements, depending on how far along the sun was in its life cycle. If that failed to happen, the collapse would continue until a new form of pressure took over: electron degeneracy pressure, the quantum mechanical resistance to compression found in white dwarfs. But that's a story for another chapter. On the flip side, suppose the fusion rate suddenly spiked. Perhaps all the hydrogen atoms in the core decided to fuse at once in an enthusiastic display of teamwork. The result would be a massive release of energy, increasing the pressure dramatically. The sun would begin to swell, its outer layers puffing outward, cooling as they expanded. The star would become larger, redder, and less dense. On its way to becoming a red giant dot again, nature does not allow this to happen unchecked. The system seeks balance, and any deviation from equilibrium triggers mechanisms to restore it. If it can dot, this balancing act does more than just hold the sun together. It also determines its structure. The temperature, pressure, and density at each layer of the sun are set by the need to balance gravity and pressure. That's why the core is so hot and dense. It needs to generate enough energy to support all the layers above it. That's why the surface is so much cooler. It only needs to support the thin layers above it and radiate energy into space. And it's not just the sun. Every star, regardless of its size, follows the same principle. Massive stars have stronger gravity and therefore need much higher core temperatures and fusion rates to stay balanced. They burn through their fuel quickly and live short, brilliant lives. Smaller stars burn more slowly, their fusion rates lower, their lives longer, sometimes trillions of years. In all cases, hydrostatic equilibrium sets the pace and the path. Interestingly, this balance also affects the life cycles of stars. As a star exhausts its hydrogen fuel, it must find new sources of energy to maintain equilibrium. The core contracts, heats up, and begins fusing helium into heavier elements like carbon and oxygen. In more massive stars, this process continues, fusing progressively heavier elements until iron is reached. At that point, fusion stops being an energy-releasing process, and gravity takes over for good, leading to collapse and, depending on the mass of the star, either a supernova, a neutron star, or a black hole. But the sun is not a massive star. It is, in cosmic terms, a gentle, middle-aged star, about halfway through its main sequence life. Its hydrostatic equilibrium is stable, its fusion reactions well-behaved, and its output remarkably constant. For us, here on Earth, that constancy is a blessing beyond measure. It gives us seasons, daylight, weather, and warmth. It allows ecosystems to evolve, civilizations to flourish, and people to plan picnics with some degree of confidence. The balance between gravity and pressure is not something we see or feel directly. It's not something we can touch or measure with a household thermometer. But it is the reason the sun exists in its current form. It is the silent agreement between the forces of collapse and the forces of creation. A compromise between destruction and light. And perhaps That's the most beautiful part of all, that at the core of the sun, where matter is torn apart and remade, where temperatures soar and particles collide with unimaginable force, there is peace, not stillness, but balance, a cosmic harmony sustained not by chance, but by the very laws of physics. It is this balance that has lit our skies for billions of years. It is this balance that will continue to shine for billions more. So the next time you look up at the sun, casting shadows on the ground or setting the clouds ablaze in hues of gold and crimson, remember this: you're witnessing equilibrium. You're seeing the result of forces held in perfect tension, of chaos woven into order. You're watching a star that has found its center, and in doing so has become a source of life, warmth, and wonder. Its gentle warmth is not the result of permanence, but of balance. And in time, that balance will shift. The story will move forward. The sun will take on new forms in its quiet journey through the ages. For now, though, we're in the golden years. The sun, in its prime, shines down on a world full of life and wonder. And for billions of mornings yet to come, it will continue to rise, reliable and radiant, lighting the way for whatever future unfolds beneath its gaze. The sun, as majestic and life-giving as it is not alone in its fusion work. Across the galaxy, stars of every size and temperament are busily fusing elements in their cores, turning hydrogen into helium, helium into carbon, and carbon into even heavier elements, all while releasing the energy that lights the universe. Our sun may be a gentle and relatively mild-mannered star, but the cosmos is filled with overachievers, stars that are many times more massive, more volatile, and far more short-lived than our familiar yellow dwarf. These massive stars live fast and die young, burning through their nuclear fuel in the blink of a cosmic eye. But their lives, brief though they are, help forge the elements that make planets, people, and all the wonders of chemistry possible, while our sun uses the proton-proton chain to carry out fusion. These larger stars often rely on a different fusion mechanism, the carbon-nitrogen cycle, more commonly known as the CNO cycle. This reaction chain is more complex and requires higher core temperatures than the proton-proton chain, which is why it only dominates in stars more massive than the sun. The CNO cycle still converts hydrogen into helium. It's just like the proton-proton chain, but it uses carbon, nitrogen, and oxygen nuclei as catalysts, temporary holders that help the process along, but are ultimately regenerated by the end of the reaction. In this cycle, protons are fused onto carbon nuclei, transforming them step by step through various isotopes of nitrogen and oxygen, before returning back to carbon and releasing a helium nucleus in the process. It's a bit like borrowing your neighbor's ladder to paint your house. You use it for a while, move up and down with your paintbrush, and when you're done, you give the ladder back. The job is finished, and the ladder is unchanged, ready to help someone else. In the same way, the carbon nucleus ends up exactly where it started, but along the way, it has helped fuse for hydrogen nuclei into one helium nucleus, releasing energy in the process. The CNO cycle is highly temperature sensitive. Its fusion rate increases dramatically with temperature, much more so than the proton-proton chain. This means that as a star's core heats up, the CNO cycle can quickly become the dominant fusion process. In massive stars, the core temperatures are often above 20 million degrees Celsius, making the CNO cycle an efficient and powerful engine. As massive stars burn through their hydrogen at a breakneck pace, they quickly progress to fusing heavier elements. Once hydrogen is depleted in the core, the star contracts under gravity, the temperature rises, and helium fusion begins. This is known as the triple alpha process, where 3 helium nuclei combine to form a carbon nucleus. From there, the fusion reactions build heavier and heavier elements. Carbon fuses into oxygen, oxygen into neon, neon into magnesium, and so on. creating a sort of elemental ladder inside the star dot. Each step up this ladder requires higher temperatures and pressures. The star becomes layered like an onion, with each shell fusing different elements. At the very center is iron, the final stop on the fusion express. Iron, unlike the lighter elements, cannot release energy through fusion. It actually absorbs energy. So when a star's core becomes dominated by iron, fusion grinds to a halt. There is no more outward pressure to balance the force of gravity. The key, in that moment, equilibrium collapses. Key, the core can no longer support itself, and it collapses in a fraction of a second. The outer layers come crashing down, rebounding off the suddenly rigid core in a cataclysmic explosion. Supernova. These explosions are among the most energetic events in the universe. In just a few seconds, a supernova can release more energy than the sun will emit over its entire 10 billion year lifetime. Supernova do more than just dazzle the cosmos. They create the heavy elements that make up much of the periodic table. Gold, silver, uranium, and dozens of other elements are born in these brief, furious moments of stellar death. The iron in your blood, the calcium in your bones, the iodine in your thyroid, all of it was forged in the heart of a massive star or in the shock wave of a supernova long ago. We are quite literally made of stardust. Some supernova leave behind exotic remnants. The collapsing core has enough mass. It can become a neutron star, a city-sized ball of neutrons with the mass of the sun, if it's even more massive. The core may collapse into a black hole, a region of space so dense and with gravity so strong that not even light can escape. These remnants are extreme, fascinating. It's fundamentally different from anything our sun will ever become. Our sun, as we've gently explored, does not have the mass needed to go out with a bang. Its death will be a quieter affair, a slow puffing away of its outer layers, leaving behind a white dwarf. But in a way, the violence of other stars has already shaped our sun's story. The cloud of gas and dust from which the sun formed was enriched by earlier generations of stars that exploded, scattering the elements they made across the galaxy. Those elements gathered together again, coalescing into new stars and planets into us. This idea that every generation of stars builds upon the ashes of the last is one of the most humbling and beautiful truths in astronomy. The universe is not static. It is an ongoing act of creation and transformation. Each star, no matter its size or lifespan, plays a role in this grand recycling process. The light from those stars travels across vast distances, sometimes for billions of years, to reach us and tell their stories. Even in distant galaxies, we can observe stars of various types and ages. Some are just forming, their fusion engines only just beginning to ignite. Others are nearing the end of their lives, pulsing or swelling or dying in spectacular displays. And among them all, our sun shines as one unassuming participant in this grand cosmic ballet, a quiet star, but one with its own part to play in. Comparing our sun to these more massive stars, we gain perspective. Our sun is neither the brightest nor the dimmest, neither the youngest nor the oldest. It is, in many ways, average. And yet, from that averageness comes extraordinary stability. Because of the sun's moderate mass, we enjoy billions of years of steady light and warmth, a luxury that many planets orbiting more massive stars may never have. Massive stars may be glamorous. They burn brighter, live faster, and die more dramatically, but they are also tempestuous. Their intense radiation can strip atmospheres from nearby planets. Their short lives give little time for complex life to emerge. In contrast, sun's slow and measured pace has nurtured Earth through eons of change, giving life time not just to survive, but to flourish. So while it's fascinating to marvel at the fireworks of supernova and the exotic remnants they leave behind, There's something equally awe-inspiring about the quiet consistency of our own star. It reminds us that there is strength in stability, power in patience, and beauty in the seemingly ordinary. And still, the story continues. Across the galaxy, stars are forming, fusing, and fading. Each one contributes to the vast web of creation that spans the cosmos. Our sun is part of that web, one node in an intricate tapestry of energy and matter, life and light. As we look up at the night sky and see the stars twinkling from across the gulfs of space, we're not just seeing distant points of light. We are seeing the past. We are seeing chemistry in action. We are seeing the engines of fusion at work, shaping the universe, one element at a time. And in that quiet, twinkling brilliance, there is a message that everything is connected, that every atom has a history, and that somewhere in the heart of a distant star, the seeds of future worlds are already being formed. So the next time you look at the sun, let it remind you not just of its own quiet fire, but of the great stellar family. It belongs to a family of fusion, of light, of creation, a family of stars, some still shining, some long gone, but all part of the same incredible story. Every morning, when the sun rises above the horizon and casts its golden light across the landscape, it's easy to take it for granted. It's the warmth on your face, the glow that illuminates the sky, the subtle shift of shadows, all feels so familiar, so automatic. But behind this daily miracle lies a vast and intricate truth. Nearly everything we see, everything we eat, everything we breathe, and everything we are depends in one way or another on nuclear fusion happening 93 million miles away in the heart of the sun. Solar fusion is not just a scientific curiosity. It is the foundation of life on Earth, from the tallest trees to the smallest microbes, from ocean currents to weather patterns, from ancient civilizations to the glow of a campfire. Everything is woven together by the quiet, steady pulse of the sun. Let's begin with something green. Plants. Without the sun, they could not exist. Plants use sunlight to carry out photosynthesis, a process that converts carbon dioxide and water into glucose and oxygen. This is not just a side project. It's the primary method by which energy from the sun is captured and stored in living systems. The glucose provides energy and building blocks for the plant's growth, while the oxygen is released into the atmosphere. It's giving us the air we breathe. When you look at a tree, you're seeing sunlight stored in wood. When you bite into an apple, you're tasting sunshine transformed into sugar. Even the scent of freshly cut grass or blooming flowers is, in some quiet way, an echo of the sun's light. Through photosynthesis, solar energy enters the food web. Herbivores eat the plants, carnivores eat the herbivores, and everything, eventually, circles back to the sun. But the influence of the sun goes even deeper. Long before humans ever walked the earth, ancient plants and microorganisms captured solar energy in their tissues. Over millions of years, as they died and were buried under sediment, their remains transformed into coal, oil, and natural gas. These fossil fuels are quite literally the stored energy of ancient sunlight. When we burn them to heat our homes or power our cars, we are releasing energy that was first captured hundreds of millions of years ago. It's a curious thought. The gas in your car, the coal in a power plant, the electricity in a light bulb, all trace their lineage back to photons born in the sun's core, released through fusion reactions so long ago that dinosaurs still roamed the earth when the light finally reached the surface. Even our bodies are sustained by sunlight. The carbohydrates, fats, and proteins we consume all originated from photosynthetic organisms. Every cell in your body runs on energy derived from food, which in turn came from plants or animals that ate plants, of course, relied on the sun. There's a poetic irony in the fact that we spend our lives under the sun, using its light to see and move and grow, all while being powered by the energy it gave us long before. In a way, we are walking solar batteries, moving, thinking, dreaming collections of sunlight turned into flesh. But fusion's influence isn't limited to biology. The sun also drives the climate and weather. When solar radiation strikes Earth, it heats the surface unevenly. Equatorial regions receive more direct sunlight, while the poles receive it at a slant. This uneven heating sets the atmosphere in motion. Warm air rises at the equator and moves toward the poles, while cooler air sinks and moves toward the equator. These movements create wind patterns, ocean currents, and the complex dance of clouds, storms, and seasons. The sun also powers the water cycle. It causes water to evaporate from oceans, lakes, and rivers. The vapor rises, forms clouds, and eventually returns as rain or snow. This cycle shapes the landscape, nourishes crops, fills reservoirs, and quenches thirst. It's easy to forget that even the gentle patter of raindrops on your window is a gift from fusion, indirect, yes, but essential. Our cultural and psychological lives are shaped by the sun as well. Humans have worshipped the sun for millennia, building temples to its rising, tracking its movements, and celebrating its return at the solstice. The sun has been a symbol of life, power, clarity, and rebirth in nearly every civilization. We measure our days by its rising and setting. We schedule our activities around its presence in the sky. Even our mood is influenced by its light. Seasonal affective disorder, for example, is a reminder of how much we need sunshine, not just to see, but to feel whole. And then there's time. The Earth's orbit around the sun defines the year. The tilt of our axis relative to the sun gives U.S. seasons. The rotation of the Earth facing toward and away from the sun gives us day and night. Our calendars, our holidays, our sense of morning and evening, all are based on our relationship with a star burning in the sky. Light from the sun has also shaped our technology. Solar panels capture photons and convert them directly into electricity. As the world moves toward more sustainable energy sources, we're increasingly turning back to the sun, looking for ways to harness its power more efficiently. Solar farms now dot landscapes across the globe, quietly converting sunlight into energy. In space, satellites rely on solar panels to keep their systems running, drawing power from the same light that filters through your bedroom curtains. The sun has even helped us understand our place in the universe. The study of sunlight, its spectrum, its variations, its interactions with Earth, has led to countless scientific discoveries. By observing how sunlight is absorbed or reflected, we've learned about the composition of our atmosphere, the ozone layer, and the greenhouse effect. Sunlight helps us monitor climate change, track weather patterns, and study other planets. And speaking of other planets, without the sun, there would be no planets at all. Our solar system formed from a swirling disk of gas and dust collapsed under gravity. At the center, the sun ignited. Around it, the remaining material coalesced into planets, moons, asteroids, and comets. The heat and light from the sun shaped their surfaces, their climates, and their chemistry. Mars once had rivers. Venus has a runaway greenhouse effect. Earth, balanced just right, found itself in the habitable zone, the narrow region where liquid water can exist and where life as we know it could begin. It's remarkable. Really? How many different threads of existence tie back to that one process? Nuclear fusion, a reaction that happens quietly, constantly, in the sun's core. A process that doesn't roar or crackle, but releases energy gently, steadily, and reliably. And that energy spreads outward through the layers of the sun, across the vacuum of space, through the sky, into our world. Into us. It is fusion that lights the morning dew and powers the hum of bees. Fusion that drives the winds and carves the coastlines. Fusion that warms your coffee, your home, your skin. Fusion that gave rise to the forests, the fields, the oceans, and the cities. It's fusion that made possible the first breath of a newborn and the final sigh of an ancient tree. So the next time you step into the sunlight, pause for just a moment. Feel its warmth. Close your eyes. That heat began in a place you will never see, in the heart of a star. In the delicate dance of particles, in the quiet conversion of matter into energy. That light is not just brightness. It is nourishment. It is movement. It is life. You are, in the most literal sense, solar-powered. You are a symphony of atoms, once forged in stars, and now fueled by their light. Every heartbeat, every thought, every smile is made possible by a fusion reaction that began over 4 billion years ago and continues to this day. Quietly, faithfully, brilliantly. The sun does not shine for us, of course. It shines because it must, because physics says it will until the day its fuel is spent. But in that shining, in that relentless giving of light, we find our meaning. We are the children of fusion, and we carry its fire in everything we do. For as long as we have looked up at the sun, humans have dreamed of harnessing its immense power here on Earth. The idea is as simple as it is ambitious: to replicate the very process that powers the star's nuclear fusion and use it to generate clean, nearly limitless energy. No carbon emissions, no dangerous long-lived radioactive waste, no dependency on fossil fuels. It's pure, radiant power drawn from the most abundant elements in the universe. It almost sounds too good to be true. And in some ways, for now, it still is. But the dream of fusion energy isn't a fantasy. It's a work in progress, an engineering and scientific challenge of breathtaking scale. It's the same forces that allow fusion to occur effortlessly in the heart of the sun become extraordinarily difficult to reproduce in the controlled environments of human technology. But the rewards are so profound that scientists and engineers across the globe have spent decades, many lifetimes, pushing the boundaries of what's possible. This is where fusion research becomes a symphony of precision and innovation. There are two primary approaches to fusion energy: magnetic confinement and inertial confinement, each with its own set of challenges, technologies, and fascinating quirks. Let's begin with magnetic confinement, which is the more mature of the two. The most well-known design in this category is the tokamak, a donut-shaped device that uses powerful magnetic fields to confine plasma in a circular loop. Inside a tokamak, deuterium and tritium are injected and heated until they become plasma. Superconducting magnets then create a magnetic field that holds the plasma in place, preventing it from touching the walls. The goal is to maintain this plasma at high enough temperature and pressure for long enough that fusion reactions begin to occur in meaningful numbers. When deuterium and tritium fuse, they form a helium nucleus and a high-energy neutron. The neutron escapes the magnetic field and can be captured by a surrounding blanket of material, transferring its energy and generating heat. That heat can then be used to produce steam and drive turbines, just like in a conventional power plant. Tokamaks have been around since the 1950s and have steadily advanced in complexity and performance. The largest and most ambitious project to date is ITER, the International Thermonuclear Experimental Reactor, currently under construction in southern France, a collaboration between 35 countries. ITER is designed to be the first fusion device to produce more energy than it consumes, a milestone known as ignition or net energy gain. Once complete, ITER will be the size of a small building, with magnets weighing hundreds of tons and a plasma volume of over 800 cubic meters. It will use deuterium and tritium fuel heated by a combination of microwave and particle beam systems. The goal is to produce 500 megawatts of fusion power from 50 megawatts of input energy, a 10-fold return. If it succeeds, it won't generate electricity directly, but it will prove the viability of fusion as an energy source. Future plants based on its design could follow in the decades to come. Its motto, fittingly, is bringing the sun to Earth. Then there is inertial confinement, an entirely different approach that seeks to compress a small pellet of fusion fuel using intense bursts of energy, typically done with lasers. Enormous, precisely calibrated lasers deliver a symmetrical pulse of energy to the outside of the fuel pellet. The outer layer rapidly explodes outward, and by Newton's third law, the inner core is compressed inward to extreme densities and temperatures. The most advanced example of this approach is the National Ignition Facility, or NIF, located in California. It uses 192 laser beams to deliver energy to a target the size of a peppercorn. In December 2022, NIF made headlines by achieving a small but historic milestone, a fusion experiment that produced more energy than the laser energy used to initiate it, though the overall system still consumed far more energy than it produced. This was a clear sign that the physics of fusion work as expected. Inertial confinement holds promise for certain applications, including potential future energy production and military research, but the engineering challenges remain steep, especially when it comes to repeating the process quickly, efficiently, and reliably. Beyond tokamaks and lasers, there are other fusion concepts being explored. Stellarators, for example, are similar to tokamaks, but with twisted, more complex magnetic fields that can provide continuous operation without the need for a central current. Field reverse configurations, magnetized target fusion, and even fusion-fission hybrid reactors are all under investigation. Private companies have also entered the race, bringing a spirit of startup innovation to a field long dominated by government laboratories. Companies like Commonwealth Fusion Systems, TI Technologies, and Helion Energy are developing compact, high-field fusion devices using advanced materials and cutting-edge computing to accelerate progress. Some aim to deliver functional fusion power plants within the next decade, an ambitious goal, but one that reflects growing optimism. Investment. Despite the complexity, the motivation is clear. Fusion promises enormous advantages. Its fuel sources, deuterium from water and tritium bred from lithium, are abundant. A single liter of seawater contains enough deuterium to power a household for hundreds of years. In theory, fusion does not produce greenhouse gases, and unlike fission, it does not generate long-lived radioactive waste. There's no risk of a runaway reaction or meltdown, and the byproducts are mostly helium, a harmless, inert gas. But fusion is not easy. Achieving ignition is a feat. Sustaining it is even harder. Making it practical, economical, and scalable is the final mountain to climb. Yet progress is steady, and each milestone brings us closer to a future powered, not by burning fuel, by replicating the stars. There is something poetic about the idea that humanity might one day light its cities, power its industries, and charge its devices using the same process that makes the sun shine. Fusion is more than just a technology. It's a connection to the cosmos, a reminder that the laws of nature are not obstacles, but invitations. They challenge us, yes, but they also guide us. The journey from starfire to power plant is one of the most extraordinary quests in science. It is a testament to human curiosity, perseverance, and imagination. To replicate the sun's furnace in a magnetic cage, to coax atoms into merging, to bottle the energy of the universe's birthplaces. That is no small dream, but it is one we continue to chase. And when we finally succeed, when a fusion power plant hums quietly, lighting homes and warming hearts without pollution or peril, we will have done more than just solve an engineering problem. We will have forged a new relationship with the universe, one where we no longer burn the past, but borrow from the stars, so the next time you feel the warmth of the sun or see its golden light stretch across the floor, remember, this is the power. We seek not to dominate, but to understand, to emulate, and to share. Fusion may be the oldest light in the universe, but for us, it may also be the key to a brighter, cleaner, and more sustainable future. As steady and familiar as the sun seems to us, rising each morning and setting each evening, it remains full of mystery. For all that we've learned about fusion, light, and solar structure, there are still puzzles hidden within its blazing face and beneath its turbulent skin. But perhaps what's most remarkable about our solar observations is the perspective they offer. The sun, once seen as a deity or a mysterious disk in the sky, is now a subject of daily scrutiny and deep scientific insight. We watch its every flicker, measure its every wave, and model its every heartbeat. We have sent machines into its atmosphere, unraveled the secrets of its light, and traced the journey of particles born in its core. Yet, for all we've achieved, the sun still holds its secrets. New discoveries await in the twist of a magnetic loop, the pulse of a sunquake, or the whisper of a neutrino. Every observation leads to new questions, and every answer shines light on another mystery. In the end, to watch the sun is not just to study a star. It is to witness a force that has shaped our world in every conceivable way. It is to glimpse the engine of life, the origin of time, the beacon of our solar system. And so, after this long and winding journey through light and heat, gravity and plasma, particles and waves, we find ourselves returning ever so gently to the quiet wonder we began with. The sun, that ever-burning star, remains above us still. It's not just a glowing disk in the sky, but a living engine of fusion, a celestial clock, a maker of weather, and the spark of all that breathes. We've traced its life from its birth in a cloud of dust to its current golden middle age. We've unraveled the intricate process of nuclear fusion, explored how this fiery heart shapes our world, and dreamed of capturing its power here on Earth. We've delved into the secrets of solar storms, puzzling temperatures, and magnetic mysteries, all while gazing through telescopes, listening to neutrinos, and sending brave little spacecraft ever closer to the blaze. And through it all, one thing has remained constant: our quiet fascination with the star that never sleeps. 'Cause the sun never rests, not for a second. Its light may help us drift off to sleep each evening, but it is forever awake, burning, churning, humming softly through the silence of space. Perhaps, as you rest now, you find yourself thinking back to those gentle questions we began with. Where are you right now? Watching or listening? What time is it in your little corner of the world? Is it morning, with golden rays creeping across the windowsill, or night, with the sky dark and the sun tucked away beneath your feet, still shining on the other side? And perhaps now you wonder, after everything you've heard, did the story soothe you? Did it spark a little curiosity, or maybe even too much to fall asleep right away? If so, I do hope it was worth it, because drifting off with wonder in your heart, it's a fine way to end the day. If you've enjoyed this quiet exploration under the wing of our sleeping sun, do consider giving it a like or subscribing to the channel. It helps keep the light on, so to speak, and it lets me know you'd like more stories like this to accompany your evenings. Wherever you are, and whatever the hour, I wish you peace, rest, care, and just enough curiosity to carry into your dreams. Of course, always remember, this is for relaxation and wonder, not medical advice. Sleep well and let the sun keep watch.